Hello and welcome to the IEEE Spectrum Online presentation, Simulating a Medical Device Interaction with a Biological System. I'm Dexter Johnson and I'll be moderating today's presentation. Before we start our presentation, I would like to mention a few housekeeping items. For those of you using Chrome and Edge browsers, if you have Flash blocked, please click on the play button on the media player. For those of you who want to know if this session will be archived, the answer is yes. It will be archived and will be available for review within about 24 hours. Once the archived webinar is available, a notification email will be sent to all the registrants. We encourage questions, and I hope we have time for several, which we'll take at the end of our presentations. As your questions occur to you, please type them in the box provided on your computer screen and hit the submit button. You don't have to wait until the end of the presentation to begin submitting questions. If you are looking for the PDH certificate code, this will be given in a slide at the end of the presentation. As you look over your screen, you should also see buttons that allow you to enlarge the slides if you so desire. And about volume control, if you're listening to the audio over your computer speakers and you need to adjust the volume, you may need to adjust the master volume on your computer. At the bottom of the slide in front of you are a couple of additional widgets that will improve your viewing experience, including a green resource page to the far right with today's presentation. Now I'd like to introduce our presenters for today. We have Paul Belk of Abbott Corporation. Paul Belk has a PhD in medical physics and is a principal engineer at Abbott, where he works on the development of diagnostic and therapeutic medical devices. He's been using simulation of all types for more than 20 years as an integral part of the research and development process. For the past 4 years, he's been using the COMSOL Multiphysics software, whenever he gets a chance, to study the physics of heat transfer and fluid dynamics in tissue. Also, we have Valerio Mara COMSOL. Valerio is the marketing director at COMSOL in Burlington, and previous roles include working in applications, technical support, and sales. He's been at COMSOL since 2008, and Valerio received his PhD in fluid machines and energy systems engineering and his Master's of Science in Nuclear Engineering, focusing on numerical methods for CFD. So let's move on. Today's agenda, we will be looking at modeling a medical device and interacting with physiology. We'll also have a live demo where we'll be modeling a catheter ablation from a large vessel. We will discuss how multiphysics simulation can boost medical device design, and we will show the COMSOL Multiphysics whole software suite. There will be a Q&A, and we'll provide information on how you can try out the software. And with that, I will turn it over to Paul to begin the presentation. Thank you.
Thank you, Dexter. The fun and fascinating part of multiphysics simulation is it lets us explore how a few simple interactions can lead to complex, intricate, and sometimes unexpected behaviors. But it gets a little bit less fun when we realize that we're betting human lives on how well we understand those behaviors and what brings them about. But that's what we have to do when we make medical devices. Of course, having lives depend on assumptions isn't limited to medical device engineering. Any aeronautic or civil engineer can tell you that. But there are some challenges that are unique to biomedical simulation. The first challenge is specifying characteristics of materials. In our case, the materials are largely tissues, and finding those characteristics can be difficult. However, happily, I can show you that most of what we need for these kinds of simulations has been and continues to be the subject of pretty productive study. Less happily, the external values, what we think of as boundary conditions in simulation, aren't always stable, and they can be difficult to predict. But I think one of the greatest challenges to biomedical simulation is that biological systems invariably contain multiple internal feedback loops. Medical devices also often contain feedback loops to try to get stable control. And so one of the things you're looking for is feedback loops that you don't control interacting with feedback loops that you think you can control. And they can interact in undesirable ways. Finally, a significant challenge in biomedical simulation is the challenge of validation of the simulation. Studies in animals are generally considered the gold standard for real data, but the issue here is that making measurements in living systems is often very difficult, and so the animals can be very opaque models. And even if you can do a good job measuring animals, it's important to remember that animals and humans can differ in significant ways, so generalizing from an animal to a human can be as bad or as dangerous as generalizing from the wrong equation. Nonetheless, we get a great deal out of simulation. Because of the challenges, sometimes quantitative predictions of behavior are difficult, but they're often very accurate in any case. But even when we have to make assumptions and operate in a partial quantitative fog, the simulation can be extremely valuable because it allows us to watch which interactions are occurring and which interactions are the most worrisome because of the breadth of information we get out of simulation. So the point is, we work for the best numbers we can get, but what's really critical to us is the insight that we can get from watching the interactions unfold during the course of the simulation. The example that I'm going to use here is a very simple study of RF ablation in a piece of tissue that's adjacent to a blood vessel. As a bit of background, RF ablation is an essential tool in many medical specialties. You can think of it as surgery without a knife because its purpose is to remove tissue that's causing disease from inside the body without having to cut down to that tissue. What happens is intermediate frequency RF energy is delivered near the target tissue, and that RF energy induces currents in the tissue itself that causes resistive heating of the tissue to a lethal temperature, usually somewhere between 45 and 55 degrees C. Often the RF electrode is introduced through a blood vessel, so the heat transfer involved is both diffusive and convective. And what we're going to ask here is, if we make a thermal lesion using RF energy in this way from within a blood vessel, how well can we predict those thermal lesions, and what are, if any, the internal mechanisms of the body that might undermine our control? Before we go to the simulation, let's fill in a couple of blanks. First, it's important to understand that what medical people call RF ablation isn't really RF in the physics sense. In COMSOL, you won't use the RF module because the frequency we use for ablation is about 400 kilohertz, which doesn't even make the bottom of the AM dial on your car radio. That gives you a wavelength of about 1 kilometer, which is quite a bit larger than most patients. And as I said before, everything you need to know about the tissues to run these simulations is compiled in an extraordinary database that's maintained somewhere in Switzerland. This is the URL to that database. And I'll show you what the site looks like. This is a list of all the tissues alphabetically. And you can see up at the top there is a frequency. Come on. That you enter in, and it'll give you what amounts to the RMS characteristics, the RMS electrical characteristics of the tissue at that frequency. And it'll also give you things like the heat capacity and the thermal conductivity, and it will even give you the metabolic heat transfer units that can be used in COMSOL, though it's in different units from what COMSOL uses. So, for the rest, we're going to build a quick simulation in COMSOL and see what it tells us. My plan is to walk through the setup of the model, which you're going to see is extremely straightforward, and see what happens to our careful designs as we start incorporating the kind of physiologic variation that the body might throw at us. Once we see what happens, we're going to try to build up a slightly more sophisticated design to see how we might accommodate those variations, and then COMSOL is going to show us how well our design worked. So, I need to back up, and let's go to the live part. So I'm not sure if there's a correct place to start a console model, but I usually like to start with the geometry because that gives me a feel for what I'm trying to put together. In this particular case, what I'm going to simulate is a piece of liver with a blood vessel going through it and a catheter introduced through that blood vessel to deliver RF energy. I don't need to build an entire liver because ablation is a local phenomenon. So what I'm going to do is I'm just going to build a cylinder of liver tissue. I'm going to call it liver. And I'm going to set up a size. I've stored these parameters in a parameters file. You can always enter numbers if you want, of course. But for me, I prefer to have them in a parameters file because it makes things much easier to read and it makes them much more flexible. So we're going to have the liver go along the horizontal axis, which seems a little bit more intuitive. We'll build that, and yes, we've got a cylinder. Now this is not completely cylindrically symmetric, but close enough, because the next thing I'm going to build is going to be centered on the same thing. It's going to be my blood vessel. I'll call it vessel. And all I need to change about that is the radius. So we'll build that. And then I'm going to duplicate that. So you see you can very quickly set up symmetric geometries in COMSOL. And this is going to be my shaft, the shaft of the introducing catheter. And that's going to have we're going to parameterize that radius a little bit differently, and it's going to be half as long because it only goes to the middle. Now I need to put an electrode on this, and I'm stealing the electrode from the COMSOL heat transfer example of ablation. We're going to make the electrode look like a trocar that extends out of the shaft. So I can't do that with a cylinder, but I can do that with another simple primitive element. We'll use a torus here, and I'm going to call that electrode. And that's going to be its curvature, and that's going to be its radius. And it's only going to go halfway out, so that's 180 degrees. And we'll need to move it up by that curvature. And I believe if we make it go in the y-axis, it'll work. And it looks like. So let's go in and take a look at what we just built. And it's backward, but that's fine. We can rotate it through 180 degrees. And yes, that worked. We are now actually almost done building the geometry of the system I'm going to simulate. I'm going to do a few more things almost as bookkeeping. First thing I'm going to do is I'm going to duplicate that electrode. No, not delete it. Fortunately it asked. I'm going to duplicate that electrode, but I'm going to make it shorter. I'm only going to go for the last 30 degrees, and I'm going to call it TC. And that is going to be a monitoring point for me. And you can see it just showed up there. Now I'm going to back out. We'll look at the whole thing. And I'm going to notice that I don't really need to look at this entire region. I don't need to simulate the whole thing because it's pretty much fourfold symmetric. And so to save myself some trouble, I'm going to cut just one quadrant out of this. This isn't necessary, but it'll be convenient in the long run. So the first thing I'm going to do is I'm going to group everything I built so far into one unit. I do that with a union, and I say just give me everything, which I did by typing Control-A, and we'll build it. And then I'm going to put in a block that will represent my back quadrant. I'm going to call that my quad block, and it's going to have the radius of my system and the length of my system. And then if I get all of this right, we obviously want to start in the same place as the system. And have the same axis as the system and build it. And okay, I did not get that right. Let's make this over 2. There it is. And I'm going to form an intersection between those two. Now you don't have to do this, but it'll make the simulation a little bit easier if you decide to. So let's build everything, and there it is. So now, by chopping out the 3/4 that really does the same thing as this 1/4 does, I've made life better for myself in a couple of ways. First of all, I've got a smaller system to simulate, so everything's going to go faster. But second, by chopping into this area here where all the action is really happening, I now don't have to look inside something to see what's going on. The most interesting things will be happening on this surface. And when we start graphing it, we'll see how useful that can be. Now I have to assign material properties here. What they call materials, we call tissue. And that, again, is pretty easy. First of all of these materials have properties that I essentially entered in by hand by copying numbers off that website and giving them names. But you only ever have to do that once, because then you put it in the user library and you can just use it. So, liver is this big block here. Blood is this area inside the vessel. We make our electrodes out of a combination of platinum and iridium. And for this, I had better zoom in. And that's you, and you, and, oh, come on. There, that seems to be everything, except I don't want to override my liver. All right, we need to zoom in here a little bit more. Got you. Okay. That's metal, and finally, we're going to make the catheter shaft just out of nylon because it's not very interesting. Now we're ready to go and do the physics. Multiphysics is fun, and in this particular case, we've got 3 kinds of physics that are going to go on. We've got fluid flowing, because there's going to be forced convection of heat. We've got electric currents, which is what generates the heat resistively. And we've got diffusive heat transfer. So we can do all of those at once, but I find it's much easier to do them one at a time and test them. So laminar flow is our first interface. It's only going to be on the blood. And we need to set up some boundary conditions. So let's go back out. That's going to be our input, and we've just set up a flow rate there, which is laminar, because this is part of a longer vessel. And that's going to be our output on the other side. Oh, that's not right. Okay. Input. Good. Outlet is here. And then, because we chop this thing into blocks, we need to tell it that these aren't real walls. These are points of symmetry. And having done that, go back to our default view and bring up a study and check and see if it works. And with any luck at all, okay. So it's given us a plot, and we'll go in and check that this all makes sense. And of course it does. It's laminar flow. We've got slow near the edges, we've got fast near the center, and this electrode is disturbing our flow as it should be, and as will contribute to our results later on. So great, that worked well. Now we need to put in the heating. The heating is through electric currents. So the electric currents interface is going to be all domains, except I will take out my little piece of nylon because I didn't specify conductivity for it. If you try to do electric currents in something for which you haven't specified a conductivity, it will give you errors, and you'll have to give it some tiny conductivity or just ignore it, which is what I'm doing now. The initial value is voltage of 0. That makes sense. For ground, we're just going to ground the outside of the slab because that makes sense. Potential is very low by there. So I'm going to click 1, 2, 3, and then I'm going to use a little trick for specifying boundary conditions. By pushing this thing, I can say outside bounds and it will remember that name as that group of boundary conditions, because I'll want to use it later. But I can do something even more. I can go and find that definition here, and I can say, take everything that's continuous with it by slope. So it also grabs my end pieces. That's handy for me. So now we've got ground. Having done that, I need to specify a voltage. And I parameterize my voltage here, but I need to say where I'm applying that voltage. And I'm going to apply the voltage to my electrode. And this is going to be slightly tricky just because I have to now click into those domains. But, so, fortunately, by using the mouse wheel, I can select domains that are under other, boundaries that are under other boundaries. And gets that done. And so now we can test that. So I'm going to turn off flow. I'm going to turn on electric currents, and we'll do a quick test of this. Okay. Because it's showing me velocity. Yes, so that's a reasonable potential. Now the action begins. We're going to turn on the bioheat interface. The bioheat interface is going to cover all of our materials, even though only 2 of these materials are biological. So by default, it assumes everything is biological, and then we will override it. First thing, initial values, body temperature 37 degrees C, that's good. Thermal insulation is the default boundary condition, but we'll be overriding that. So we've got 3 kinds of materials here. We've got liver, we've got fluid, and we've got non-living materials. So the fluid is just our blood there. And we specify, in this case, the fact that it's fluid just means that it's going to move heat convectively. And we specify that the velocity is what we calculated when we did our laminar flow. So it fills this in for us. The solid, in this case, means solid that doesn't metabolize. So I'm going to go in again, and I'm going to mark up these regions here that are my electrode and my catheter shaft. Temperature here is a boundary condition. So obviously if I'm putting heat in, I've got to take heat out, and I'm going to take heat out through exactly the same boundaries that I was taking current out through. Symmetry, I've got bigger symmetry boundaries here, but I'll use the same cheat that I used last time. I'll create a symmetry boundary. I'll go up and I'll say grab everything that's continuous with it. So that creates my symmetry boundaries. Again, we put in symmetry to remind it that the world doesn't end at the edges of these blocks. It's just this is where the action is happening. And finally, I need a heat source. And the heat source here is from the electric currents interface, and this QRH thing just means this is the energy that comes from resistive heating. And that heat source is going to be everywhere except my handle, in which there is no electric field. So now the entire thing is set up, I believe, and it's time for us to try to simulate it. So in this particular case, I'm going to do a parametric sweep. So remember I talked about the usefulness of using parameters. I've set the blood flow to be F sub V, and what I'm going to do is I'm going to simulate different strengths of blood flow from 0 up through something just below nominal to something just above nominal, and see what happens when I apply heat, see what kind of thermal lesion I get. So here we'll just push the equal button. And while this is baking, let's talk about what we've done. So the first point I want to make is the geometry I set up was extremely simple. In fact, if you wanted to, COMSOL would let you take a CT scan of a segmented liver and enter the entire thing in. There are a couple of reasons I don't normally like to do that. The first is, whoever CT scan that is, your next patient is going to have a different CT scan, so you don't want to build a device just for a single patient. But the second is, when I keep it simple like this, and this does encapsulate most aspects of the physics, then the physics takes front and center. I never wonder whether some effect I'm seeing is due to some really strange piece of geometry that I took the trouble to simulate. So in this particular case, even my electrode is very simple, but it does allow me to study the physics, which is heating by the injection of current. Now, the multiphysics that's going on is I've got conductivity, which varies with temperature, interacting with current, which is creating heat, which is diffusing out through here, and which is being carried away by blood flow, which is moving at a velocity which is determined by doing laminar flow. So every one of those processes is very simple on its own, but the processes, the way they combine, is less simple. So let's see what's happening here. And the action all right. There we go. So this is the case where we have no blood flow at all. That's not a very interesting case biologically, but it allows us to take a look at the essential symmetry of the system. And as you can see, it's a little bit asymmetric because the electrode's a little asymmetric, but it's not a huge surprise. It's very hot in the center, and it cools down to our lethal temperature just about here. Now what happens when we turn blood flow on? A couple of very interesting things. Number one, of course, your symmetry is gone. This is very surprising to some people, but here's the thing that's most surprising to people. The hot spot, you'll notice, doesn't even touch the electrode. That's pretty non-intuitive. People think the electrode is the source of power. It ought to be the hottest. As we increase blood flow a little bit more, not surprising, everything gets cooler, so our lesion changes size. So what does this give us in terms of insight? The insight here is the heat sink from the blood is so powerful that it completely moves our lesion away from where we think it's going to be and detaches it entirely from the electrode. The other piece of insight we get is, not surprising, if the body throws more blood flow at us, our lesion changes size. We don't want that, and so we're going to try to compensate for it by building in a feedback scheme. Now, this is something that COMSOL can do, and it's also something that I can do because of a trick shown to me by my friends at AltaSim. Step one is to turn on advanced physics options, which I like to do anyway because it makes me feel advanced. Step two, I'm going to turn on a component coupling, and I'm going to tell it to use this thermocouple domain that I used. Come on, there we go. And step three, I'm going to turn on this global equation. And let's expand this so we can see what the equation is. And now I'm going to push the button. And while we're waiting for this to bake, oh dear. Now let's see if it works. Now, so I'm going to go back to one where the result is already existing. So what I did here, first I will show what we did here. So the component coupling that I turned on averages something in this region, and I have chosen to average temperature. So down in bioheat, in this equation here, what I've done is I've set up a simple equation where I take the average of the temperature across that domain, and from that I subtract my set point temperature, which is 45 degrees C, or 45 K plus 273 K. And I have told COMSOL that in addition to all of the other equations that it minimizes for its finite element work, I would like it to minimize the value of this equation. And I can specify that equation anywhere I want. I chose to put it here. And I said the tool that it can use to minimize that equation is it can change the voltage that I apply to this electrode. So I've created here temperature feedback. The idea was if blood is cooling the system too much, it's also cooling my electrode. So when I see increased blood flow cooling my system, cooling my electrode, I want to respond by increasing the power. And my hypothesis is if I can keep this region of my electrode at 45 degrees, then I'll have a nice stable lesion out here at about 50 degrees independent of blood flow. So let's see how that hypothesis did. I'm going to open the plot and everybody gets to put down their bets on how much better we did. So here we go. First thing we look at, parametric solutions. Right. So here we are in the case of zero flow. And if you look at my 45 degree isotherm here, we've done a very nice job of keeping my thermocouple at 45 degrees. Of course, we've made no lesion at all because, as we know, when there's no flow, the blood is the hottest region, not anything near the blood. That's okay. A patient with no blood flow needs more than an ablation. So let's see what happens when we turn blood flow on. And here, this is looking pretty nice. Once again, my thermal control is working. You can see my 45 degree isotherm running right through the center of my thermocouple, and there's a nice lesion. Now I'm going to increase the blood flow. And my hypothesis is that I ought to get about the same size lesion because now I'm controlling for the thermal cooling. Okay, is there anyone who thinks that this new lesion is the same size as this old lesion? As a matter of fact, if you look carefully, the surprising thing you're going to see is that the variation I was trying to correct when I was using old crude voltage feedback was smaller than the variation I've introduced by putting in this new temperature feedback. This is an extremely surprising result, or at least many people I've shown this to are very surprised. So, for those of you who saw this coming, congratulations, you're very good at this. But a lot of engineers didn't, because what's happening is I put in what I assumed was negative feedback. And my simulation has shown me that I wandered into a parameter space in which negative feedback turned into positive feedback. Why? Because the cooling effect of the blood operates differentially on the thermocouple more strongly than on the tissue. So now, the more cooling there is, the hotter and the larger this lesion becomes. So this is where I want to close my part of the demonstration on the value of using simulation in something like a biological system where a lot of times you don't have a great deal of control. The point here is that this was an obvious feedback mechanism. If you're having trouble stabilizing the temperature, measure the temperature and stabilize what you measure. And because of the physiologic variation, we see that it actually works against us. The point of simulation is you can try these experiments in an animal, but it would be very difficult to elucidate this result clearly, because even if you could measure the temperature everywhere in an animal, which is a difficult thing to do, you'd also have to measure the flow and correlate it with every lesion you create. And if you do all that, you've got to hope that the animal is going to give you a wide enough range of flows. You can do it on the bench, which would be a better idea. But if you're going to build a bench system to do these kinds of measurements, it's probably a good idea to simulate it first anyway to see how it's going to work. And the last part of that circles back to the major benefit I see of simulation in a complex system, especially a biological system where it's so difficult to know everything that's going on. And this is a benefit that accrues before you ever push the calculate button. And that benefit is that by setting up the simulation, you're forced to systematically consider what effects seem to be important and how they're going to interact with each other. And just by setting it up, you're reminded of that discipline. And then if you do push the calculate button and you get the simulation out, you can get insight because you can study systems like this. You can study results like this, even when other parameters are relatively poorly controlled. And by studying them, you can say, okay, now I understand why that thing I built and stuck in that animal didn't behave the way I thought it would behave. I need to watch this particular parameter much more carefully. So with that, I will give it back and stop the screen share.
Thank you so much, Paul. This is Valerio from ComSol. It was a great live demo. We learned a lot of things, and I see lots of questions coming in. So I just wanted to stress a few things and Paul some time to rest before the Q&A at the same time. And you know, what we see happening in the medical industry with our customers using ComSol. So as you might have guessed, there is, it can be used to physical prototyping. You can test new ideas in this virtual world of simulation. Before you have to physically construct something, you can learn a lot of things. And in an industry like this, where safety is also paramount importance, the capabilities to investigate different scenarios, boundary conditions, material properties, physiological mechanism will allow you for a early, harmless correction of any design mistakes or problems. And this is what Paul was also talking about. Another aspect that we see is helping engineers and physicists and physicians even dealing with biomedical device design and in general bioengineering and using simulation is that through simulation you can access the value of a variable in any place in your model. It could be temperature, velocity, and basically you could even try to understand better your experimental data when you compare them to simulation results. And then everything boils down to the ability to access values, numbers, intuition, insights in locations where it would be impractical sometimes, if not impossible. You will be able to place a sensor or disturb the environment around the sensor and then affecting the measurement. So lots can be gained when you use simulation. Lots of insights can be gained again. And another point that I want to make is the body, as it is a multiphysics system. We are a multiphysics system, and everything influences everything else. And medical devices, then they have to be designed in such a context to function properly and effectively. And what multiphysics simulation does will allow you for high fidelity modeling. But what do we mean by that? Well, it means that if there's a physical effect that you have to include, you can do it. So if you have to couple together heat transfer and fluid dynamics, you can do it. If you have to couple also then EM, electromagnetics, you can do it. You can do it in the way it happens in the real world, which means you can let your model grow in complexity and get closer and closer to a realistic description of what you want to model or what you want to understand. So I totally subscribe to Paul's point of view. You start simple, you get insights, and as you get better both at understanding your system and using the software and taking advantage of simulation, you can include more and more effects to see what is going on. So just while I was talking, I was showing you also a few examples. And also, we didn't talk about it today, but what you can also do with ComSol is build the user interfaces on top of your model, so you can hide the complexity of your simulation, of your mathematical model, and let other people simulate their boundary conditions, scenario, you name it, geometric parameters in a controlled environment. So you just put together an interface for them where they can input numbers, run a simulation, and get an understanding of what is the device that they're working on. So that's also another possibility. And just to give you a little bit more insight into the architecture of COMSOL multiphysics, you saw COMSOL multiphysics interaction, and COMSOL was using the model building part of the software. But then you can just click a button, and from within the same interface, you can then build apps, which we talked about. And then if you go back on the model building, you can create lots of different physics. It can be fluid, EM, heat transfer, structural, chemical, acoustics. You can input your own equation. That is very important. For some applications, you have to be able to use your data. It could be temperature-dependent materials or a particular structure mechanics model. You can also optimize, and very important, you can integrate COMSOL with CAD software, so you can import more complex geometry, even if most of the times you're good to go since the beginning with the capabilities that we have in COMSOL to create geometries. But again, as soon as your model advances, you might want to get into using different geometries. We can import meshes, scans, as Paul mentioned, and then you can also connect to Excel. You might have material properties there. Whatever data you have can be used in COMSOL, and then we can connect to MATLAB. So just want to say a few words again about what we see the industry is doing with the software tools and a little bit about the architecture. And I think now we have plenty of time for a few questions.
Okay, great. Thank you, Valerio, and thank you, Paul. Just before we get to the questions, I'd just like to put out the product suite as a point of reference while we're going through the questions. So, Paul, we have a number of questions here for you. Maybe some of them you've already responded to this person specifically, but I think we can ask them, the general audience, these questions as well. So how did you add TC control equation inside the bioheat transfer physics?
Okay, well, again, I want to thank my friends at Ultisim for showing me how to do this, and they had to show me more than once. But if you go to the eyeball up here, there's a lot of stuff that's turned off by default, and one of them is the advanced physics options. So the first thing you do is you turn on advanced physics options. Having done that, when you right-click on the bioheat interface, and I think most of the interfaces, you come down here to global, and you can add a global equation. So a global equation just means, in addition to all of the other equations that I'm implicitly solving because of what you specified in the physics module, here's an equation that you can specify yourself. So I added the global equation, and I named it, in this case, TC control. And then up here, I did a component coupling that I called TC average, and I went over this fairly quickly. But what this is, if you look at the type, you can add, under definitions, there are things called component couplings, and I added an average component coupling. So once I did that, it put something up, and I renamed it to TC average for thermocouple average. And what this type of component coupling does is it takes a piece of geometry and it says, I will average values within that geometry. So I've named it TCAV, and we go down to this equation, and you see I say TCAV of T. So I'm saying I would like you to average the measured temperature everywhere across this domain. And then I would like you to subtract from that temperature 45 degrees C, which I broke out into Kelvin here because C doesn't work for some reason in this context. And this is an equation that I want to be 0. This is an error equation. So please make this difference as small as you can. And the way I want you to make it small is I want you to adjust the voltage on my electrode until this equation is as small as you can make it. So it's a feedback control system. COMSOL naturally does feedback control because the way it minimizes the errors for its finite element simulations is by driving parameters until the values of the error equations are as small as possible. And feedback's nothing more than an error equation.
Okay, great. Before we go to the next question, I'd like to address an issue that we had earlier. There were two PDFs in the resource page widget. One is a booklet that COMSOL has, and another one was today's presentation. I think what we were missing was the presentation. So if you refresh your browser, you should be able to see the PDF of today's presentation. Let me go back to a question here. So, Paul, your simulation suggests that laminar flow, the ablation hotspot, is downstream slightly. Does this suggest positioning the catheter electrode tip offset from the desired ablation point?
It could if you have that's actually a very good point. That's something that I didn't mention, that the flow creates not just a radial asymmetry, but a longitudinal asymmetry. And yeah, you have a little bit more extent downstream from the catheter tip because the blood is a little bit warmer. In practice, those sorts of variations are relatively small compared to the size of the lesion you're looking for. So I have never seen anyone suggest that, though it's a good suggestion if you're trying to do really precision stuff. Often what people are most interested in is the depth of the lesion. And that's why I focused on how deep it went rather than how far down it goes. But you make an extremely good point. The lesion is asymmetric, and if you're trying to do precision, and people are trying to do more and more precision with their ablation, that would be a very good thing to take into account.
Okay, we had a question that came in a little earlier that I may have overlooked. The question is, could you decompose the temperature control implemented in the electrode tip? More specifically, the equation used for the feedback. So let me say that again.
Decompose it? How do you mean?
You get it? Decompose the temperature control implemented in the electrode tip, or specifically the equation used for the feedback.
All right. I might have covered that the last time through, but let's look at it again. The equation itself is actually very straightforward. I have to create an equation whose expected value is 0. So I want to give it two components across a minus sign, and I want those components to be equal. The first component I gave it was the average temperature on my thermocouple, which I created using that component coupling. And the second element, I should say, in the equation was just a number, a set point temperature, with units of degrees K. And so I said, please take the average temperature across the thermocouple domain and make that as close as possible to the set point that I've given you in degrees K.
Okay. I think we're still sort of, there's your, did you want to add any points now that your demo is up on the screen?
Yeah. So there's two elements to this equation, separated by this minus sign here. The first element, TC_av of t, is what the simulator does for me when it uses this coupling here to take an average of some parameter. Now, when I created this average coupling across this region of geometry, it said, okay, I'll average anything I know. So I could average temperature, I could average voltage, I could average blood flow, even though there's no blood flow up here, anything. When I set up the equation, I said, okay, the thing I want you to average is temperature. And that's on one side of the minus sign. On the other side of the minus sign is my set point. My set point is 45 degrees C. But here I wrote it out in Kelvin because this is happier with Kelvin temperatures. So I said it's 45 degrees plus 273 degrees. So it wants the result of this subtraction to be 0. It wants this average temperature to be 45 degrees. And what it will do is it will change the voltage that I put here until this equation is 0. So it's a very basic feedback equation. I'm setting it up. But it has, the components it has are something that it can measure. In other words, something that will change as the simulation evolves, and something that it controls, which in this case is the voltage. If I set this up so that I wanted it to modify the conductivity of blood until this was true, probably my simulation would never converge, because that's too hard a problem for the simulator to solve. But this is a simple problem. Make the voltage smaller until the temperature gets, until this average temperature gets close to this.
Okay, let's just keep that up on the screen for a second. I think I have another question that's in the same vein and may require you to use the demo again. Yeah, you mentioned modeling a temperature dependence on the conductivity, but
yes,
the value from it is database or single values. How do you use that value to create the temperature dependent equation?
Okay, well, the easiest way to do it is the electrical conductivity is generally a number, but COMSOL doesn't limit these sorts of parameters to being numbers. They can be functions. So I didn't go over it, but this is actually an important thing to do when you're studying ablation. Here you see that when I specify the properties of blood, for example, I specify the electrical conductivity not as the default 0.734 Siemens per meter, which is what blood is, but as something I called AN1 of T. And so I go back up to my definitions, and you see here I have a function, blood conductivity. And I've defined that function as 0.734 Siemens per meter times 1 plus 2% of however much the temperature is above 310 degrees K. Because empirically, in solutions where the conductivity is ionic, aqueous solutions where the conductivity is ionic, we know that it goes up about 2% per degree K. So now what COMSOL needs to do is it looks at this T, which to COMSOL means temperature, and says, all right, when I am solving my electric currents and my resistive heating, the first thing I need to do is I need to look at the conductivity of some little piece of blood. And I do that by looking at the temperature of that piece of blood and then looking up the conductivity in this equation. So that's how I did that.
All right, great. Valerio, let's we could sort of circle back to you. I have a question here about this product suite. It looks like a very powerful and comprehensive suite of tools. Can you briefly describe the learning process and how long does it take to become productive?
Oh, that's a great question. I'll give an answer and then I'll ask Paul to comment also. So when you get the software, there's what we call application libraries that go with it, and that's a collection of hundreds of models in different physics that fully solve and document it. So basically, it could be a self-learning process. It's also true that if you're a customer, we have support, technical support, and we can answer any question you might have. Plus, we have classes. But what I see that is very powerful is you find a model that is close to your application, and believe me, it will happen because we have many models. And then you start, playing with that one because it's something that you would understand. It's a physics that you know, a problem that you might know very well. And then, you can expand it and add new features and new complications on top of it. So that's how I see, customers learning. The learning is more about, I believe, the modeling. How should I model my problem than use the software? Because I have to say that that we pride ourselves in how usable it is, how easy it's very few clicks. You have all the options right in front of you. So it's more about what you want from your model. At that point, it's very likely that you can implement it in COMSOL. And if we didn't do it for you through a specific boundary condition or whatever, very likely you can describe it with an equation, and again you can input it. So I think it's not a difficult process. Of course, it will take some time. So we have the tool to help our customers. Forgot to mention videos. We have lots of videos, lots of tutorials. So we have plenty of material that people can use. Paul, what's your take on it?
Well, if the question is how long does it take you before you can become productive, I would say that's measured in days. You're not going to be an expert. Well, I don't know that I will ever be an expert in simulation. You can always learn more. But the way COMSOL is set up, you can start getting insight into simple problems fairly early on. One of the points I tried to make with this demonstration is if you put together 3 cylinders and a torus, you can already begin to learn somewhat surprising things about the way resistive heating interacts with convective heat transfer. So the more you learn, obviously the more sophisticated questions you can ask. But when I began learning how to do this, I found that I was destroying incorrect assumptions that I had made about the system within the first couple of weeks I was working on it. And I think that is an extremely valuable thing to be able to do in simulation.
Okay, great. I think we're going to move on to you, back to you, Valerio. I know we have some slides, and this sort of addresses the question of how we can learn more. So I'll hand it back to you.
All right, thank you then. So yes, we have plenty of resources, as I mentioned before. We have books that you can download from our website as PDFs about how to use Multiphysics, how to build apps, manager's guide if you want a high-level overview, white paper and books. Plus, we report on the success of our customers and users, so you can read what fellow simulation specialists do with the software. Additionally, you can meet us in person. We did lots of COMSOL days so far this year. There's one more in Columbus, Ohio coming up. And that's a full day where you meet again, other people interested in simulation, COMSOL people, there's talks, mini courses, and it's a free event. And if you want even more, we have a conference in Boston is coming up, plus other cities worldwide. That's a longer event, so there's more opportunities to learn, connect with COMSOL employees, again with fellow engineers, and there will be talks, keynotes, panel discussions, the poster session. So it's a mix of everything. It's a good balance. We go from presenting people presenting their work in a poster or oral sessions to hands-on mini courses to again keynotes and panel discussions. So there's a lot of to bring home and think about. And to get in touch with us is very easy. You go to comsol.com/contact, and we can also show you, do a personalized demo for you, and you have a link there, it's /request-a-demo. If you're a user, I strongly suggest to stay current, to update to the latest version of the software. We're at 5.3a. Easy, go to comsol.com/product download. And again, there's lots of content that does not require any password or any access. To just go to our website and just grab it and see what you can learn from it, and hopefully will also inspire you to do better product design. So I just want to thank you, Paul. It was great, and thank you, Dexter. I don't know if Paul has any closing remarks for today.
No, I don't think so.
Okay. Well, thank you both. Great presentation. I just want to, I know a lot of people are interested in getting this PDH code, the certificate code, so this is now out there. So we are out of time. As I indicated earlier, this session will be archived in about 24 hours, and once the archived webinar is available, a notification email will be sent to all the registrants, and that includes everyone here today. I'd like to thank both our presenters today for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session, and we hope you will return for future IEEE Spectrum webcasts. Thank you.